general relativity, step by step. Last time I finally pinned down the form of the metric tensor in the presence of a gravitational wave, and it is, no it isn't, it is the flat space metric alpha beta plus a small perturbation, which was of this form here given by the sum of these two matrices. What I'm going to do now is ask what happens to a particle in a gravitational wave. Well, to answer that we need to know, well, a free particle, I guess. A free particle follows a geodesic motion. And so from screencast, I think it was number 48, we've got the following equation: d2x alpha by d tau squared, that's supposed to be an alpha, that. Oh no, it's this. Alpha plus u beta u gamma times Christoffel symbol alpha beta gamma equals 0. And that's the geodesic equation from screencast number 48. Here, x alpha equals the position of the particle. Tau equals proper time. U, and then whether it's a beta or a gamma, let's say a gamma, is the 4 velocity, and this is the Christoffel symbol. Well, that's quite difficult to solve. So what I'm going to do is to simplify it in much the same way that we simplified the Einstein field equations by considering the linear case. I'm going to consider a simplification of this. So for the 4 velocity, I'm going to choose 4 velocity. Well, I'm going to choose it to be at rest. And you'll remember that the 4 velocity for an object at rest is just that. So let me recast my equations here. Let me just explain, I'll just open it up a little bit. Alpha by d tau squared plus sigma over beta and gamma. You see, because the beta and gamma are summed, u beta, u gamma, Christoffel, alpha, beta, gamma. And the alpha's free here, so it equals 0. So we've got four equations here. But if we specify that the particle's at rest, then we know that u is this 1 0 0 0. So that tells us that because it's at rest, beta equals 0 and gamma equals 0, because if either of them are not equal to 0, we're multiplying by one of these zeros here, and we've got no contribution. So that tells me that d2x alpha by d tau squared equals Christoffel symbol alpha 0 0. Oh no, it's not. It's equal to minus that, isn't it? Because it's this plus this equals 0. Okay, so we need to evaluate this for a gravitational wave. Let's just get on with that. Alpha beta gamma equals, from the definition, alpha pi times di g d di x do plus di g b x dot minus di g d by di x d. What have we got? The pi sums on the first, it sums on the second, it sums on the bottom. What have we got left? We've got beta and a gamma, which go beta and gamma, gamma and beta, gamma and beta. Now, yes, because we're in the linear regime, I may as well consider the flat space metric, eta. You'll remember eta 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. That's eta. So effectively that tells me I may replace my this is summed over pi, of course, but it doesn't matter if pi is not equal to alpha. So I may as well just get rid of pi if I can. Why is it not deleting? Let me, there we go. That's alpha. Alpha, no sum now, because I'm evaluating it. So that pi there, I'm having some problem with my erasing. Yes, that should be alpha beta. That should be gamma alpha here, because I'm replacing pi with alpha. G, I've forgotten what it was now. It's got to be alpha gamma, hasn't it? And this one down here is a dialpha, of course. Dialpha. Okay, equals alpha. Well, now what I want to do, well, keep alpha free, no sum over alpha there. Now I'm going to specify that beta equals gamma equals 0 because of the 4 velocity condition here, which I originally imposed. The particles are at rest to begin with. So that tells me that Christoffel alpha 0, 0 equals a half eta alpha alpha, and alpha can be 0, 1, 2 or 3, times beta equals gamma equals 0. So that's di G alpha 0 by di T plus di G alpha is free, gamma is 0 by di T. It's T because beta equals 0 gives me the variable T there. Minus, and then this term here is di G gamma beta 0, 0 by di. Well, at this point, I don't care what that is. Well, I may as well write it in anyway. That's di T. But the form of the metric I'm using, if I can go back to it here, it's got the transverse condition. So there's zeros on this row here and zeros in that column there. And it's the same with this term here. So that means that this term here is equal to 0. And it means that that term there is equal to 0, and it means that this term here is equal to 0. So all in all, we've got 0, 0 equals 0. Let me rephrase. Let me go back to the geodesic equation, which I'm going to write down here. d2x alpha by d tau squared equals minus Christoffel alpha 0, 0, which equals 0. What? So there's no acceleration. That means no acceleration for a free object, a free particle, in a gravitational wave. Wait, what? What I'm probably expecting to see is what I'm expecting to see classically at least, is that it's like being on the sea, floating on the sea, and a wave comes past you and it makes you accelerate up and down. But we don't see this. We see d2x alpha by d tau squared equals 0, so there's no motion. However, so it looks like we've wasted our time. And indeed, this is a sticking point, or has been a sticking point for physics for a very, very long time. Gravitational waves were of uncertain, not on a certain basis, they were on an uncertain footing for about 50 years after Einstein published the field equations. And this is one of the reasons why, because there's no local acceleration. But all this means, is we have constructed a coordinate system in which freely falling objects, I'll say particles because they haven't got any length scale. Freely floating particles are at rest. We can always do that. Here's me, and I'm saying to myself, well, you know, I'm expecting these black holes to collide any minute, and I'm going to have a barrage of gravitational radiation. And I'm a little bit worried about my fish. Here's my fish. Is that a fish? Doesn't look much like a fish, does it? Let me draw the fish first, and then the fish tank. There's my fish. Still not very good, is it? There's my fish in the fish tank, and I'm worried about... There's the fish. What does the fish look like? There you go. And this fish is in a fish tank here. And I say, I'm a bit worried about my fish because this gravitational wave is going to come through and the water's going to slosh about. And she won't like that. So I say to the fish, listen, I'm really worried about this. What's going to happen when these black holes collide and we get deluged by a gravitational wave? And the fish says, well, easy, duh. Do what any physicist would do. You build an elevator around yourself, and then you can construct some coordinate systems in which space is nice and Minkowski. So light travels at the speed of light and everything just works nicely. The gravitational waves come by, but because I'm in my elevator, I am not aware of them even, if my elevator is small enough, and my fish is all right. She just sits there. There's no way locally you can tell that the gravitational wave is passing by. All from the equivalence principle. The equivalence principle is an absolutely amazing piece of logical thinking. You use the equivalence principle over and over and over again in different contexts. You use it mathematically and you use it physically. It doesn't matter what's going on. There could be black holes, there could be all sorts of terrible things happening, and all you have to do is to build an elevator around yourself and pretend that it's not happening. And you can get away with it because you can construct a local orthogonal system. So gravitational waves, all that's happened is we've constructed a coordinate system in which objects which are at rest remain at rest. So it's a kind of inertial coordinate system. It's a coordinate system that makes motion easy. So it looks as if gravitational waves aren't real. However, if you've got two objects at a particular distance from one another, well, then we might start getting some non-local effects, because they can build, these people in these little particles here, they can build elevators for themselves. And sure, physics is locally Lorentzian inside here, but there's a long distance between these two elevators here, and something peculiar might happen to that distance, because space itself is stretching and squashing. And I'll cover that in the next screencast. Stop.